nuclei in the alpha state and the number of nuclei in the beta state. Well, again, we've got our splitting diagram. We know our energy relationship to the applied magnetic field. Delta E is equal to H gamma D naught over 2 pi. We know that delta E is 0.120 joules per mole for a proton. We can take that energy and basically plug it into the Boltzmann distribution. So that ratio must be equal to E to the power of all of this stuff minus 0.120 joules per mole divided by the Boltzmann constant, let's say at room temperature for the sake of argument. Avogadro's number, everybody knows Avogadro's number, 6.022 times 10 to the 23rd. We get this ratio, 0.99995, which it's always hard to put into real terms, so let's try and put that into some kind of understandable sense. For every 100,000 molecules that are in the lower energy state, for that energy splitting, we've got 99,995 in the higher energy state. So the difference here is minutely small. Let's think about what that means. Okay. So in terms of visible spectroscopy, think about a Jablonski diagram. We've got two energy states. We think of essentially all of the molecules that are in your flask is in the lower energy state. We apply some light. We promote one of these electrons to the higher energy state. Whether it's singlet or triplet doesn't really matter in this case. This one's probably more correct. Okay. Now you've got population difference because you've applied that light pulse. You've now got some molecules in the higher energy state that you didn't have before. Okay. But this kind of simplified analysis requires that you tell yourself in your mind that all of your molecules in a UV vis or an infrared spectrometer experiment are in the lower energy state. That's not the case here. Here you have essentially almost the same number of nuclei in the lower energy state that you have in the higher energy state. Okay, which means that this kind of simplified picture of promoting from a lower energy state to a higher energy state doesn't really apply. But the same kind of idea is true in that if we apply a frequency pulse, which is in exactly the right, which has exactly the right energy between the two energy states, we can still perturb the difference in population. Okay, you're not absolutely changing it, but you are perturbing it, and that's important. Okay, I want you to remember this is really, really small. Again, it's amazing that NMR works. It's amazing that you can actually get some useful signal given that you're dealing with such a small energy difference, which means that you have such a small, minutely small population difference. Okay, you wanted to add something?
Yeah, so imagine what you could do with the sensitivity if you could change that proportion. So there is one case where they've done it. Xenon 129, if you hit it with a laser, you come out with a much longer lived difference in proportion. So you can activate Xenon 129. Now it's pretty much useless for most people.
But the principle is cool.
Yeah, the principle is cool, yes.
Yeah.
So they're looking for ways to do that. That will be one of the next big advances. They can find a way to do it to a lot of different things.
Mm-hmm. The other thing that you can do to help yourself a little bit, we're going to talk about ways to improve the sensitivity a little bit, but you'll notice that temperature appears in here. So if you change the temperature, you can help yourself out a little bit as well, up to a point. That's where cryoprobes and things come in. So,
No. Cryoprobe's not changing the temperature of your sample.
oh no, it's cutting the noise.
Yep.
Yeah, sorry.
Yeah. There you're still stuck with whatever the range you're allowed by your solvent.
Yeah, that's true.
And sometimes actually the EMR itself. When you've got equipment trying to get through all of these different things, it doesn't necessarily have a good temperature range.
Okay, so you've got a difference in energy. That difference in energy, it turns out, corresponds to the radio frequency range of the electromagnetic spectrums. Not in the visible range, not in the infrared, you're way down in the radio frequency range. Very, very small energy difference. Okay. When you apply a radio frequency signal that matches the resonant frequency for your nucleus of interest, your distribution between the nuclei in the bottom state, nuclei in the top state, will be changed when you hit that resonant frequency. Okay. That's going to cause your nuclear magnets to precess in the magnetic field. Precess means swing around, basically. We're going to talk a little bit more about what that magnetization vector looks like in a minute. Don't worry about it right now. I'm going to get to that point. Okay. But your nuclear magnets are going to be precessing in the magnetic field. Okay. That basically allows you to do spectroscopy, and NMR at some level is essentially absorption spectroscopy. It's a little bit fancier than that, as we'll see in a minute. NMR in principle can be done in two different ways, either continuous wave NMR or Fourier transform NMR. Nobody anymore, well, no, that's not quite true, but you guys do not do continuous wave NMR. But a lot of the terminology that you use comes from continuous wave NMR. And so in order for you to properly understand all the terminology that we're going to be using here, it'd be useful if we can start with a little bit of an explanation of continuous wave NMR first, and we'll move into the Fourier transform. So it's also easier. Okay, so in continuous wave NMR, we're going to vary either the frequency or the field. You can actually do either one if you think about them, okay? While holding the other one steady. Okay? And essentially, we're doing an absorbance experiment. We're exciting some nuclei that are in the lower energy state to the upper energy state, and then we're detecting an emission with a receiving coil. Okay, it's kind of like doing fluorescence or absorbance in spectroscopy. Okay, it's a very small proportion of that energy that's applied that's essentially taken up, but it's enough that we can detect it in a radio frequency receiving coil. Okay, that's going to give us a spectrum. Okay, we could plot that spectrum any way we want. Okay, and as NMR has moved through the decades, people have actually decided to plot it in different ways. Nowadays, pretty much everybody plots the NMR spectrum the same way that you would plot a UV-Vis spectrum, the same way that you would plot an infrared spectrum, which means that you decrease frequency as you move to the right. If that seems backwards to you, shouldn't necessarily. Think about how you plot a UV-Vis. You always plot in terms of increasing wavelength, so decreasing frequency as you move to the right, okay? So decreasing frequency goes this way, increasing frequency goes that way. Now, in the older continuous wave NMR instruments, it turned out that instead of holding the field constant and changing the frequency, which sort of seems the obvious way to run this experiment, it turned out it was easier and more accurate to hold the frequency constant and change the magnetic field, okay? And so the terminology tends to reflect that change in field. So increasing field goes this way, decreasing field goes that way. That's why the stuff on the right-hand side of your NMR, we talk about being upfield, and the stuff on the left-hand side, we talk about being downfield. Okay? So upfield is the smaller numbers, downfield, bigger numbers. Sort of seems backwards, but that's where it comes from. Okay? Stuff that's on this side of the NMR, we talk about as being shielded. Stuff that's on the other side, we talk about as being de-shielded. Talk about where those terms come from in just a minute. Okay? So that's your basic NMR spectrum. Okay? Think of it very much like the UV-Vis absorbance spectrum. Okay? You want to comment?
After you get into Fourier transform.
Okay. Oh yeah. Fourier transform NMR. Okay, so like I said, if you go downstairs, you're not running a continuous wave anymore because it's simply not sensitive enough. Okay. So when you go downstairs to run an NMR spectrum, you're using a Fourier transform NMR. That's what most modern instruments are built around. There are some reasons still to use continuous wave. You don't need to really get into that today. So basically in a Fourier transform NMR, you're applying the frequency signal, a single powerful pulse, covers the whole frequency range. So you're essentially irradiating with all of the frequencies that you want to use at the same time. This lasts for a time that is on the order of a few microseconds. Okay? Now, what happens? Let's remember that your